All right, guys, let's talk about algebraic proofs and some properties and things today. So, 16th lesson of the semester. Yeah, yeah. Good, because that means you're enjoying yourself and it's wonderful.
I'm enjoying myself.
Come on, give me a little something. All right, algebraic proofs. So we're going to go over some properties of algebra that you use every single time you solve an equation. You just don't tell me what property that is. With a proof, the idea is when you're solving an equation, then you have to tell me what property you use to justify that step. So your reasons or your justifications are the properties that we have. When we get into geometric proofs with segments and angles, we're going to have reasons and what rules of geometry or algebra allowed me to do the things that I do to prove that two angles are equal to each other, or that this angle is perpendicular, or this line is perpendicular to another. So we're going to kind of learn the process today. So we're going to go over those properties of equality that we use, but we don't ever say that that's what we're doing. So the addition property of equality, what it says is if A equals B, then A plus something is equal to B plus the same thing. So you're adding the same thing on each side. So if you add to each side in order to solve the equation, then your step is justified, or your reason for making that happen is the addition property of equality. Guess what the subtraction property of equality does? Subtracts on each side. So if you subtract on each side to solve an equation, then you're using the subtraction property of equality. So anytime you do that step, when you're solving one of these equations, you're writing a proof for it, you have to tell me what property that you're using there. So if you add, it's addition of property of equality. If you subtract on each side, subtraction property of equality. And then multiplication property of equality, guess what you're doing to each side? You're multiplying each side by something. Yeah, A times C and B times C. The division property of equality, guess what you're doing? Dividing both sides by the same thing. So A divided by C equals B divided by C. So anytime you use that operation to solve a problem, then you are using that property of equality, and that's the reason or the justification for a particular step. The distributive property, if A parentheses B plus C, then A parentheses B plus C equals what? AB plus AC, right? Distribute whatever's out there. So if you do a distributive property part of a problem, we don't ever tell that's what we're doing, but that's what we're doing. We need to write that in our reason for doing that. And then we get into some of these little lesser known properties that we don't do as much with, or don't say we're doing as much with. The substitution property. So if A equals B, then A may be replaced by B in any expression or equation. We use that when we're evaluating length of segments and stuff like that. We use that when we solve systems of equations. We use the substitution property. Been teaching that, taught that in Algebra 2 this week sometime. And then the reflexive property. This is, again, one that we don't use as much. The reflexive property for any real number A equals A. Something's always equal to itself. That seems like, why would you ever use that? Because you're not saying anything. Well, yeah, you are. When you're proving things, you need to say, okay, if you ended up with 3 equals 3, then you need to say, hey, reflexive property, 3 does equal 3, or something to that effect. The symmetric property, and this one and the reflexive property, for whatever reason, get mixed up a lot, and people use the wrong one for what they're doing. With reflexive, it's a mirror. It's exactly the same thing on each side. With symmetric, it turns it around. So if A equals B, then B equals A. That's what the symmetric property does. It reflects. I think the idea is that in geometry we talk about reflecting. It moves it across, and we think that changes the order. But when we're talking in algebra, the reflexive property is just an exact reflection of the same thing. So it's exactly the same thing on each side. The symmetric property is the one that swaps back the order there. Then the transitive property, if A is equal to B and B is equal to C, then what? What could we say out of that? Yeah, then A is equal to C. And we use that one a lot more than we think we do. But transitive property, it's got three pieces. One thing is equal to the same thing as another one, and so those two things are equal to each other. So these properties are going to be used not only in the algebraic proofs we're going to do today, but when we get to some segment proofs, they're going to be used. We get to angle proofs, they're going to be used. We get to proofs about triangles, then you're going to use these properties too. So get very familiar with them. If you'll read through them every day and familiarize yourself with what's happening there, that'll help you out as far as learning those things. All right. So know these properties by heart, not by a page of notes. So know them, okay? And like I said, most of them you're using already. You just don't ever say the name of them. All right. So when we're using these properties of equality, we can justify our steps when we're solving equations. We're going to use a two-column proof format, which is more of a secondary education style of doing a proof. When you get to college, if any of you guys major in math and you have to prove someone's theorem or whatever, you're not going to use a two-column proof. You're going to use what's called a paragraph proof, which takes full sentences and all that stuff. So a two-column proof is much, much easier to do.
Are we going to have to do that?
Paragraph proof? No, we're not going to do that. Two-column proofs are what we're going to do in high school. If you majored in math in college, you might have to do a paragraph proof. That's what my geometry class in college, that's all paragraph proofs. The whole class. It was awesome. No, it was actually good. The professor was good. The geometry was kind of boring because I already knew it. It was proving the things in the proper way is kind of the idea of the course out of that. So that's kind of where we're headed with this. So it's two-column proofs is the format we're going to stick with. And on EOC, I know that this is what happens is they do two-column proofs, and they might have like a drop-down box where you pick, well, it's on paper this time, but so it'll be like multiple choice. You pick what goes into each box out of that. But it'll be a two-column proof style out of that. And they do ask those questions on EOC. So this is definitely something we need to work on. So the left side of the two-column proof are going to be our statements. The statements in an algebraic proof are the equations where you've actually done the work. Okay, that's just the normal way we'd solve an equation. We can't skip steps when we're doing a proof of an equation. So we're not going to try to do two or three things at once. We're only going to do one step at a time when we go to solve here. Even though I know that you guys are smart enough to skip a few steps and do more than one at a time. We're not going to do that here. The right side are the reasons that justify each step. Okay. What can be used as a reason in algebraic geometric proofs? Things that can be used as a reason are properties, definitions, postulates, which we haven't talked a whole lot about, and then sometimes we can use theorems. We haven't got into a whole lot of those yet, but postulates and theorems are things that we'll get into when we start doing the geometric proofs. We'll start talking about postulates and theorems. Postulates are rules that always are valid. Theorems are the prefix there, or the root word is theory, and those are actually results of rules results of postulates. So theorems are ideas. You know, the most famous one that we know about is Pythagorean theorem. It's the theorem, it's not a rule. It's because of some of the rules of geometry that a squared plus b squared is equal to c squared. But properties and definitions will be mostly what we use here with algebraic proofs. We won't get into any postulates or theorems yet. When we get into geometric proofs, we'll talk about those a little bit more. And I don't have you memorize like the number of the theorem, because a lot of classes they'll have numbers to the theorems, but just knowing the name of it is important. And usually the name tells you what it does anyway. So that's how we'll approach that. So we're going to use properties and definitions today to do a lot of this stuff. So let's get into our first algebraic proof. Really short, easy equation that we all know how to solve. So the given is that 4x minus 1 is equal to 27. We are asked to prove that x is equal to 7. Okay? So set up first line of your statements should always be what you're given. The first reason should always be given every single time. So when you're doing a proof on a quiz, if you miss the first line, then you're not trying, okay? So I grade proofs line by line. So if you miss the first line, I'm sorry. It's too easy. It should always be what you're given, and the reason is it was given, okay? That's always going to be the case. So number one is always going to be given there. And then how did they get from step 1 to step 2? What was the math that happened? They added 1 to both sides, right? So what property is that? Yeah, the addition property. And we'll do of equality in parentheses. I'm not going to require you to write of equality on every one of these. That would stick with this man. I can't do it right now. Come back to me. All right. Now, how did they get from step 2 to step 3? Divided by 4. So that property is at division property. Now, in college, you would have to write out the word of equality. I'm not requiring you to do that. I think we all know that that's what it is. If you were writing a paragraph proof, you would need to write that out. So that is super easy, right? Nothing to that. Let's look at number 2. A little bit more complicated looking equation, but stepwise, it's the same. So again, the first line should be the part you're given, and the first reason should be it was given to me, or given. All right. We're asked to prove that a over -6 plus 2 equals 5. We're asked to prove that a is equal to -18. Okay. So what was the first step that they used? Subtraction property. Pretty easy. And then last step. Yeah, they multiplied by -6 to get -18. So that's the multiplication property. Easy. Questions about the first 2? Hopefully there are none. You guys know how to do this kind of stuff. Let's look at number 3. And when you're having to solve the equation, you may do your steps differently, but I should be able to look at each step and your property or your reason over here and understand what you were doing. So you may not necessarily, when you go to solve the equation on your own, they don't have the steps on the left side given to you. You may do it differently because this is not the only way to solve this equation, but it's the way that they did it. So what did they do to get from step 1 to step 2? Distributive property. Their handwriting practice in today. And then what they do, get from 2 to 3. subtraction property. And then finally, division property to get from step 3 to step 4. All right, pretty easy stuff here. Let's skip on down there to number 5. It looks like a lot of fun. But it's an equation. It's only got x's in it, so it can't be too hard. It's only got one variable. Just got a lot of stuff. So step 1, they give us the given, the original problem, and they say that was given to us. We're trying to prove that x is equal to 2/3 out of this. So how did they get from step 1 to step 2? All it was distributive properties, all they did. We normally would probably do more than one step at a time. If we're solving it, since we're doing a proof, you're only going to do one step at a time. So distributive property. And then 2 to 3.
Would that be added because negative 7x plus 4?
Is it the addition property of equality? So we added something to the side,
No,
for both
it's not
sides?
on the equal side.
It's just on one side, right? So what do we call that when we put together the like term? Simplify. Yeah, that's what we want to write there. Because we didn't do something to both sides of the equation there, right? We only did the left side. They put the negative 7x and the 4x together with the operation that was there. So that's a simplify step. So your reason for that would be simplify. Yeah, you should know that in general. That's what you're doing. That you're simplifying by putting like terms together. So simplify would be the step there. And then here's the thing that's going to clue you in that you're not going to use the property of equality. Something didn't happen to both sides. Only the left side is the only side that changed. So you know it's not a property of equality. So that's usually when there's a simplify. Okay. 3 to 4. Subtraction property of equality. Because they move the 12x over there with the negative 3x. And then 4 to 5. Addition property. And then finally, division property. Not too bad. Let's look at that. Because it changed the order, right? So symmetric property. Yeah, that's right. So Caitlin brought up a good point. Looking at number 4, everything looks great. It's the same until we get to 4 and 5. And notice here, we're asked to prove that x equals 12. We know that 12 equals x means the same thing. And if we're just solving the equation, we don't do anything to that. We just leave it that way. But because the prove statement had x on the left-hand side, our answer has to have x on the left-hand side. So from 4 to 5, this would be a symmetric property of getting it. Because that's reflexive.
So
Reflexive has got to have exactly the same thing on both sides. So this would be a symmetric because you've got different things on each side and you turned it around.
Okay, so would you have even things for number 4 and 5 because you put the symmetric for 4, would you?
Now for 4, the idea it's
did.
how did you get from 3 to 4, and then how did you get from 4 to 5 goes on 5. So 5 should be symmetric, 4 would be division, 3 would be addition properties, and then 2 should be subtraction property. Get over there. So if you wanted to go through there, I'm just going to write it down. We already did it. Subtraction property, and then this would be addition property. and then the division property, and then symmetric. All right, easy enough. All right. Let's look at the next page where they don't put anything in the statements for us. Okay, we'll look at a few of these. I won't do all of them, but we'll look at a few of these and make sure we're on par with that. So what should be our first statement? All right, so I'm going to number them 3x plus 1 equals negative 14. And then our first reason should be given. Absolutely. Good job, Carson. Now, so 3x equals negative 15 to the subtraction problem. Not necessarily, no. We shouldn't need them all on this one. They just put enough there in case you did it a different way, which I don't know how else you would do this one. But so last statement would be x equals negative 5 by what property? Division. And it's okay. You don't have to use all of the boxes. Some of them they put a few extra in there just so you got room just in case. And I do number mine just in case maybe my step takes a little longer to write, or maybe I have to show some work in between or something. If I didn't want to do it somewhere else, I couldn't do it in my head. So that's pretty easy. Let's go to number 4. That looks more interesting than the rest of those do. What, you don't want to do those by yourself? Okay. All right. So number 1. Because that was bestowed upon us. All right. Number 2. Okay, so 5y minus 1 equals 14. Good. And operation that you used was the multiplication. And then 5y equals 15 by addition. Step 4 is division. Oh, they're not. They're really the algebraic proofs, you guys, because you're good at solving equations, should be. What? What part?
The S and N's and the signs.
Aw, bless your heart.
P's and Q's and R's and negative R's.
Let's go to number 6. Do number 6 real quick. So number 1 on number 6. Copy it down. And the reason.
Wait. Oh no.
So number 2 would be, so negative 42 is equal to 7n by subtraction property. And then number 3 should be, so negative 6 is equal to n division. But does that match?
No, it's a symmetric.
Yeah. It doesn't have the same thing on each side. So it's a negative 6 and an n. So those are not the same. So when you flip it around, negative 6. No. Because I'm just just turning it around, and that's that symmetric property. Throwing that symmetric in there. Part of it. Questions about those so far? Let's do number 8, because it looks like a lot of fun. Oh my God. 14 minus 2. It's not. It's a 7th grade problem. The first one's going to be given. I'm going to say this ever. Haley, you're wrong.
So then you're gonna distribute the 2.
Okay.
But it's only going to one side.
Okay. So I agree with the distribution of the -2 on the left side, but what else is happening on the right side?
A -1.
Yeah, distributing a -1. So that's going to be 14 minus 2x minus 16. And we used distributive property to get that done. Good job. Yes. Step 3, combine like terms on each side. So that's going to be -2x minus 2, and then 2x plus 34. So I'm simplifying each side by putting like terms together. And so that's what I would use for my reason.
And then you're going to add 2 and subtract.
Okay, yeah, one step at a time. We would normally try to do 2 steps if we were just solving, but if we're proving, we need to do 1 step at a time. So whether you choose to move the x's next or the plain numbers next is totally up to you, and that may change the way your proof looks compared to your neighbors. Okay, so I'm a plus the regular number first on this one. So I'm going to go to -2x equals 2x plus 36. And so my reason would be addition property. And then my step 5, that's going to be my statement. How did I get there? I did subtraction property. And then the last step, x equals -9 by division. At where it changed colors there from blue to red, at that step, I could have moved this 2x over here and then the next step moved the 34 over there with the -2. And then I would end up having to do a symmetric property at the very end. So kind of try to choose which way you're doing that. Look at the proof statement to kind of help you decide, but don't let that restrict you. You can still solve the equations the same way we've always done it, but you may have to have an extra line or something like that on your statements and reasons.
Name that property.
Yeah, name that property. Famous game. It's coming to the Game Show Network very soon. On that game? No, it's not fair for you to be on it. We need people that would make it funny. You'd get them all right, is what I'm saying, Tilly. Right? Okay.
I just said yesterday. I said that the month had 31 days in it, so.
Well, we're gonna bring it up. You brought it up. All right, number 1. Pay no attention to this extra thing I didn't crop it right. I had to stretch it out to get that one that's really long, so I got part of my letters in there. So number 1, which one of those properties is that? H, symmetric property, because it turned it around but didn't change anything, so that's H. Number 2, 2x equals 14, and then the x equals 7. Division property of equality. E. 3.
G, reflective, or reflective.
Reflexive is the right way of saying that. Because it's the same thing. 4 does equal 4, right? Always. Number 4. Addition property. That's A. 5.
It's that
Transitive. So because you have 1, 2, 3 things out of that, and it ended up being 2 things. So that's transitive property. Distributive property is correct. That's, I wrote E up here, and that was E down here. That should have been that was division property. I looked at division property and wrote the letter below it. So sorry about that. Number 7. Yeah, it looks a little weird because they wrote it beside it, and we usually write it underneath it when we're solving. And even though that's not a usual step for solving that problem, it's still legal mathematically because you're doing it to both sides. So you're subtracting 3 from both sides, so that would be a subtraction property. So they were trying to throw you a curveball there. Good job. You kept your hands back, stay inside the ball, get it to the right field. And then 8, what is it? Substitution. When W equals 1, you put that in the place of it. So substitution is F. Number 9, multiplying 10.
This is the 3 one again, the trans, right?
Transitive, yes.
Yeah. I don't know, I'm gonna say wrong, but it says wrong.
New rule, no saying that. Number 11. What's number 11? Addition, yeah, you're adding to both sides. Out of that, again, they tried to put some spin on the ball. Left it hanging. All right, for 12.
This is the symmetric.
Good job. H. And 13.
I ain't got no idea. Substitution.
Yeah, we plugged something in the place of something. So that's substitution, which is F. And 14. Is it?
Well, it would be division because 8 divided by.
Here's what you're starting with. Here's what you're ending with. Hypothesis, conclusion. What did they multiply on both sides? 8. 8 times M is 8M. 8 times negative 2, negative 16. So multiplication is what that one is, which is C. Say that again. What do you call that? What do you call it in Algebra 1? When you started with the problem? No. So you had something like 3x plus 9, and then you did this. And 1x plus, yeah. Be factoring is what it is, but what operation did you use to get it there? Division, yeah. All right, so 15 is reflexive. G16. Yeah, that would be distributive. It's just backwards from what it's written backwards out of that. So since factoring is not an option there, distributive property, which is E. Okay. All right. So in your packet there, you should have some sort of guide. Is that in there? Did I put that in there? No, that's in the segment. They didn't do one for the algebraic because it's too easy. All right. So